about how to think about neural net Jacobians. And we actually decided to switch it up. I understand normally the professor gives the research talk and the students give the primer, but I thought the students did the actual research, and so I'd give them the opportunity to tell you about it. And so I'll be talking about neural net Jacobians. And so, as I said, this is the primer for James's and Jem's talk on Lipschitz-constrained architectures. And the primer focuses on neural net Jacobians because that's really the main concept you need for understanding the research part of the talk. And so I'll be talking about what we learn from looking at Jacobians and how you compute with them and what they tell us about neural net optimization. And I'll try to limit the talk to things you can reason about just using elementary linear algebra and calculus. So there shouldn't be too much background you need for the primer. And the role of the primer is mostly to understand why we're asking the questions that we're asking in the research talk. And so if you don't get all of it, then you should still be OK for the research talk. So what is the Jacobian? This is just the Jacobian from calculus class. So if you have a neural net that computes an input-output mapping y equals f of x, so f is the function computed by the network, and if it's a regression problem, y could be a vector of scalar valued outputs. If you're trying to classify images, it could be a vector of probabilities of what that the network assigns the different object categories. And the Jacobian matrix is just the matrix of partial derivatives of the entries of y with respect to the entries of x. Right, so each entry of the matrix is one of the partial derivatives. And I'll use the subscript yx to indicate that this is the Jacobian of y with respect to x. Also talk about some other Jacobians in this lecture besides the input-output one. But this is probably the most relevant one to think about for most of this talk. And the reason we care about the Jacobian is that it defines the first-order Taylor approximation to the network's function around a particular input. So we can approximate the network's output at a point x in terms of the output at some other point x0 times plus the Jacobian at x0 times the difference x minus x0. So it's just the standard first-order Taylor approximation. And the univariate case is just the slope f prime of x. So you can use that to get an intuition for the Jacobian. And so the first thing I'll talk about is what is Lipschitzcontinuity. So it's basically the property that the outputs do not change much in response to a small change to the inputs to the network. So I'll talk about how this relates to the Jacobians of the network, and then some things that we basically get for free if we have a Lipschitz bound on the network. So I'll tell you about adversarial perturbations and estimating a kind of distance between probability distributions called Wasserstein distance. So after that, I'll talk about how to decompose the Jacobian into a product of layer-wise Jacobians for the network. So much of the research talk will be about how to design Jacobians, design layers for neural nets such that the Jacobians have particular properties. So this part of the primer will motivate why we're doing that. And then at the end, time permitting, I'll talk about what the Jacobian tells us about neural net optimization, and so how it helps us understand the problems of ill-conditioned curvature and exploding and vanishing gradients. So first off is Lipschitzcontinuity. And so the definition of Lipschitzcontinuity is pretty simple. So a function f is k Lipschitz if for any two inputs x1 and x2, the distance between the outputs of the function is bounded by this constant k times the distance between the inputs. So the function is k Lipschitz if this is true for any two inputs for a single value of k. And in measuring the distance, we have to define a norm. So probably the most common one would be the Euclidean norm. But in neural nets, we sometimes have reason to think about other norms. For example, the infinity norm, and I'll remind you what that is in a bit if you've forgotten. But basically, it's just saying that a small change to the input should cause a correspondingly small change to the output. And for continuous functions, there's a kind of simpler, or an alternative way of thinking about Lipschitz constraints. So in the univariate case, you can sort of convince yourself that the function satisfies the Lipschitz constraint if and only if the slope of the function is bounded by k almost everywhere. And so basically, the definition of a Lipschitz function says that around every point, the value of the function has to be bounded by some multiple of the distance to that point. So the function has to lie either in this region or that region. And that has to be true for every value of x. Okay? And you can sort of convince yourself from this picture that that will be true. So if it's a continuous function, that will be true if and only if the slope of the function is bounded by k everywhere. Okay? And so that's the univariate case. What's the multivariate generalization of that? So one instructive special case is linear functions. So if we're computing a linear function, f of x equals ax plus b for some matrix A, then the K-Lipschitz property is equivalent to the norm of A being less than or equal to k, right? And what norm? Well, if we use a particular vector norm for the Lipschitz property, then the norm we need for the matrix is the corresponding matrix norm. And so a matrix norm, so given a vector norm, the matrix norm is defined this way. So it's the max over vectors not equal to 0 of the norm of ax divided by the norm of x, right? Or equivalently, you can define it in terms of the max over unit vectors x, so vectors with norm 1 of the norm of ax. Right? And so if you're using the Euclidean norm, then basically the matrix norm of A will be the max over vectors on the unit circle of the length of ax. Right? So the so the matrix 2 norm is probably the canonical norm to think about, but there are other ones that we sometimes use. And so some examples are, so the 2 norm, so the vector 2 norm is just Euclidean distance, and the matrix 2 norm turns out to be the maximum singular value of the matrix. Okay? There are also other norms. So the vector 1 norm is the sum of the absolute values of the entries, and it turns out that the matrix norm, this matrix 1 norm, has what seems to be a fairly simple definition. So it's the max of the sums of the absolute values in any of the columns, right? And so from this definition, it might seem to be kind of easier to work with than the 2 norm. This sort of turns out not to be the case for neural nets. The two norm winds up being more convenient if we can't construct the matrix explicitly. But anyway, that's what the matrix 1 norm is. And then correspondingly, there's the infinity norm. So the vector infinity norm is the max of the absolute values of any of the entries of the vector. And the matrix norm winds up being the same thing as the matrix 1 norm, except replace columns with rows. So those are some canonical examples of matrix norms. So now we said that for a univariate function, the function is K-Lipschitz if and only if the slope is bounded by k at almost all values x. The multivariate analog of this is that a continuous function is K-Lipschitz in some vector norm if the corresponding matrix norm of the Jacobian is bounded by k for almost all x. And so, for instance, if we want a function to be K-Lipschitz in the Euclidean norm, it suffices to guarantee that the singular values of the Jacobian are bounded by k everywhere. So that's if the function is continuous, and it has to be continuous in order for it to be Lipschitz. Okay, so that's basically the definition of Lipschitz continuity. Why do we care about it? So I'll give a couple examples of how it's useful in neural net training. So the first example is robustness to adversarial perturbations. And so there's this really surprising property. Yep?
Do you need to introduce the Jacobian to define it? I mean, you could also just say that the distance between the inputs is about k times the distance. The distance between the outputs is about k times the distance between the inputs.
Right. So that's the definition of the Lipschitz constraint, right? But because in the research talk we'll be imposing that constraint by way of imposing constraints in the Jacobians, I think it's very useful to think of it that way also. So there's a very surprising property was observed in 2013, which is that if you take essentially a state-of-the-art ImageNet classifier, it's possible to make extremely small perturbations to the images in a way that completely confuses the classifier. And so here's an example where you can take an image of a panda that's correctly classified as a panda and add an extremely small perturbation to it. So here's an image that looks like white noise, and we're multiplying this perturbation by 0.007. So that is small enough that when you round the pixels to an integer value, it actually rounds to the same thing as the original image. So it's obviously visually indistinguishable. But if you're working in floating point arithmetic, then that's enough to confuse the network, and it's 99% confident that it's a given. And so this is what's known as an adversarial perturbation. The paper that introduced it was titled Intriguing Properties of Neural Networks. So that gives you an idea of how it was viewed at the time. And this is actually one phenomenon of several that the paper introduced. But since then, people have become much more worried about it. They've constructed adversarial examples sort of in the physical world that are robust to multiple viewpoints and things like that. And so there's been a lot of work in the last few years of trying to make things robust against these attacks. Here's just some other examples of adversarial attacks. You take basically an arbitrary image from ImageNet and make an extremely small perturbation and get the classifier to think it's an ostrich. Okay. And so I'm not going to really talk about how to defend against these things in general, but one property that would be very useful for it is if you can guarantee a Lipschitz constraint on the network. And this is a case where it's useful to use the infinity norm. So they tend to use the infinity norm for adversarial perturbations. So the infinity norm is the maximum change to any particular pixel value. And that is regarded as a better match to our perceptual detectability than the 2 norm. And so if the network is k Lipschitz in the infinity norm, then we can guarantee that a small change, the small perturbation to the image will only make a small change to the network's output. And mathematically, the guarantee it would actually give us is, let's say that we make a classification with a large margin. So if the network outputs a score for every potential object category, and there's one category I that has a much larger score than the others. So yi is larger than yj plus m for every other category j. What can the adversary do? Well, if they can perturb the image with an infinity norm of epsilon, and the Lipschitz constant is k, then the adversary can bring down the score of category I by k times epsilon, and it can bring up the score of category j by k times epsilon. So as long as epsilon is less than m over 2k, then you're guaranteed that the network will still make the same prediction regardless of the perturbation. Yep.
I think I'm actually kind of confused by these adversarial examples. I mean, it seems to be saying that so the function computed by the neural network, it seems to be saying that at every point there is some direction in which the derivative is very, very large.
Exactly.
That's very confusing to me, that these functions would be so irregular
Mm-hmm.
in general. That's a
Right,
general
right.
property.
Mm-hmm. Yeah. So this is.
Does it require that the neural network be extremely large? I mean.
So that's the right intuition. So it certainly gets much worse for larger networks. And so the adversarial attacks are much more impressive for ImageNet than they are for much smaller data set like MNIST or something like that. So smaller in terms of the image size. And it's not inevitable. So you can train networks that don't have that property. So one way is to force them to be Lipschitz. Other kinds of adversarial defenses often have the same sort of property, somehow regularize the network so that it's not, the predictions aren't too unstable. And actually, there was an excellent paper that came out last year called a Fourier analysis of adversarial examples. And so if you're used to thinking about image representations and the Fourier domain and things like that, that paper really provides an excellent intuition for a lot of different adversarial phenomena. Right. And so I say all of this with the caveat that it's still not clear whether adversarial perturbations, whether epsilon ball perturbations are a realistic threat model. There isn't really a realistic situation where the adversary would actually be constrained to an epsilon ball. And so really, this is more of a fruit fly for studying robustness in general, because these sorts of attacks are fairly easy to construct, and they're fairly powerful unless you unless you specifically try to defend against them. Right, so adversarial perturbations are one reason to care about the Jacobian. Another reason that is fairly useful is for Wasserstein distance estimation. So we work with a lot of probability distributions in machine learning, and it's often useful to be able to measure the distance between them. And probably the most common thing we use in machine learning is something called KL divergence. So it's not exactly a distance metric, but it's a measure of how different the distributions are, and it's motivated by coding theory. And if you're not familiar with KL divergence, that's okay. But one property of KL divergence is that it doesn't use the metric of the space X that the distribution is over. So if the distribution is really good at generating things very close to the data, but not exactly the data, then that doesn't count. Right? So something that is insensitive to the actual metric on the space. But for things like images, there is a natural metric structure. You can measure the Euclidean distance between images, for instance. And so the Wasserstein distance is a very nice measure of distance between probability distributions because it actually makes use of the metric structure. And it's also a real distance metric. So you have all the usual properties of distances. And so right.
It's useful for intuition for people who haven't seen this before. I think sometimes to think of the pair of delta functions at two different points, where the KL, the divergence between them is infinite. But in the Wasserstein distance, the distance is just the distance in the underlying space. Yeah,
that's a really good example. Yeah. Right, and so Wasserstein distance is essentially Earth mover's distance. So the idea is you have one pile of sand, and you'd like to transform it into a different pile of sand, and you'd like to do it in a way that minimizes the total distance that you move all of the individual grains of sand. And so that's a particular optimization problem, and mathematically, so the definition can be kind of confusing to parse, but the Wasserstein distance between two distributions P and Q is the minimum over joint distributions R over the set gamma, which is the set of distributions whose marginals over the two values are consistent with P and Q respectively. So it's the minimum over that set of the expectation of the distance between the elements drawn from the respective distributions. Okay. And, so that's the mathematical definition of Wasserstein distance. And if we want to estimate the Wasserstein distance between two distributions, it's actually pretty hard to do from that definition. So the naive idea would be just generate lots of samples from the two distributions, and then compute the Wasserstein distance between the empirical distributions. Right? So if you approximate each one with a uniform distribution over the samples, then algorithmically it's fairly efficient to compute the Wasserstein distance between the sets of samples. But the problem is that it's very statistically inefficient, because if you're working in high dimensions, then you have a lot of sampling error just as a result of the variability in which points you sample from each distribution, right?
Why is the discrete case easy? Because naively, I have to think about all the permutations, right?
Right.
Spaces and factorials, so that doesn't seem
Yeah, so I don't want to say it's easy, but so if the sets are the same size, then there's a efficient algorithm called the Hungarian algorithm for finding the optimal matching between the two sets. And if they're different sizes, there's there's some nice algorithms for doing that. There's a Sinkhorn algorithm that can find it fairly efficiently. So it's not really, it's not a computational obstacle, it's a statistical obstacle. So there's a lot of variability in which points you sample from the distributions. And so if you have two Gaussians that are almost identical, and you try to measure the Wasserstein distance between them, then it'll be dominated by just the sampling error in which points you sample. So if we want to actually estimate it, it's more common to use the Lagrange dual formulation. This is given by the Kantorovich-Rubinstein theorem. And this says that the Wasserstein distance is equal to the max over the set of all Lipschitz functions of the difference in two expectations. So the expectation of f under p minus the expectation of f under q. And so we're optimizing over the set of one Lipschitz functions in whatever norm you use to define the Wasserstein distance. And unfortunately, we can't optimize directly over the set of Lipschitz functions because there's no general compact way to represent them. What we can do instead is optimize over a more restricted set. So the set represented by a neural network with a Lipschitz constraint. Okay? And because we're optimizing over a more restricted set, it'll still be a feasible solution. So we'll have a lower bound on the Wasserstein distance. And the more expressive our network architecture, the better a lower bound we can get. And so this is the idea behind something called the Wasserstein GAN, if that's something you happen to have heard of. So basically it uses this formulation. If you happen to be familiar with GANs, this thing looks kind of like the discriminator for a GAN. So it's trying to learn a function that kind of maximally discriminates between the two distributions P and Q. And so you're simultaneously learning a generator network that tries to sample from a distribution, minimizing the Wasserstein distance. And so just like with the regular GAN, these two networks are trained simultaneously, and they're competing with each other in a min-max objective. If you haven't seen GANs before, that's OK. I only mentioned that in case it's something you're already familiar with. Right, so how can we actually estimate, or how can we actually compute Jacobian norms? Right, so if you've trained a network and you want to know what's the 2 norm of the Jacobian at a particular point, how can we do that? And one thing to observe is that the size of the Jacobian is the output dimension times the input dimension. So, so this can be pretty large. But there's one case where it's fairly easy, which is if the network has a single scalar-valued output. Because in that case, the Jacobian is just the input gradient. So the gradient of the scalar output y with respect to the input x. And that's basically the thing you compute with ordinary backprop. And so if you're living in that world, then computing the 2 norm or any other norm of the Jacobian is fairly easy because you can just compute the Jacobian using backprop. And so the way the gradient penalty WGAN works, if you've heard of that, is it imposes a regularizer on the network that requires the 2 norm of the gradient to be close to 1. So it just penalizes the squared distance between the gradient norm and 1 and puts a very large penalty on that so that in practice the gradient is very close to unit norm. So if you don't have scalar valued outputs, so if the output dimension is larger, like it is if you're trying to classify ImageNet images, so you have 1,000 different object categories, then it's completely impractical to actually compute the Jacobian explicitly. And so we have to instead access it implicitly through implicit matrix vector products. And this is a really cool idea if you haven't seen it before. So the idea is that, so we don't want to construct the matrix explicitly, but what we do is we write our algorithm in terms of the matrix times a vector or the matrix transpose times a vector. And it turns out that when you use backprop to train a neural net, what's backprop actually doing? What it's actually doing is it is computing the Jacobian transpose times a vector. And I'll say in a bit more detail how that actually works. But that's basically what backprop does, and it's essentially the same thing as reverse mode automatic differentiation. And there's also a forward mode automatic differentiation. It's used less often in machine learning, but the major frameworks like TensorFlow, PyTorch, JAX, things like that do support it. And that gives a way of multiplying the Jacobian times a vector. And fortunately, these are both linear time operations. So they're roughly as expensive as computing the function itself. And it's just one line of code in the major frameworks. And so one example of how to use this, so if you want to compute the 2 norm of the Jacobian using matrix vector products, so the 2 norm is the largest singular value. So you can compute the largest singular value by computing the largest eigenvalue of JJ transpose and taking the square root. And so you can compute the top eigenvalue of this matrix using the power method, and that just requires starting with a random vector and then multiplying by J and J transpose lots of times. And so it's really neat that even though you can't construct the Jacobian, you can still compute with it. All right, so that's what the Jacobian is and what we can do with it. And I want to make the point about how the Jacobian decomposes into Jacobians for individual layers of the network. So most of you have probably heard of the backpropagation algorithm and maybe have a very rough sense of how it works. And in general, we take what's called a computation graph of the network. So we take all of the different values that are computed on the way to computing the cost function. And so that defines the computation graph. It indicates which values are computed directly from which other values. And backprop works by sending messages called error signals backwards through the computation graph. And I'll say what the messages are in just a bit, but they basically come from the chain rule for derivatives. So you're just kind of applying the chain rule over and over in a dynamic programming framework. And what is the multivariate chain rule? Here's the calculus class version that you might be familiar with. So if we have a function f of x comma y, and x and y are both functions of t, so the computation graph would look something like this, then the sort of calculus class version of the chain rule says that the derivative of f with respect to t can be written as a sum over these two pathways, and for each one you multiply df over dx times dx over dt, or df over dy times dy over dt. So that's the calculus class picture. When we're dealing with neural nets, I like to think about it in a slightly different way. So what we're doing is we have a computation graph, and we're trying to compute the partial derivative of f with respect to each of the nodes in this graph. And we assume that we've already computed df over dx and df over dy. And what we're trying to do is find df over dt. And so when we apply the chain rule, df over dx and df over dy are values that a program has already computed. And these partial derivatives, dx over dt and dy over dt, are the derivatives of the mathematical expressions used to define that layer of the network. And so I actually like to use a slightly different notation, which uses a variable with a bar over it to denote the derivative of the cost with respect to that variable. And then the partial derivatives indicate partial derivatives of individual mathematical expressions. And so when we compute these messages, so here's a single layer of the network. So we have a vector z and a vector y that's computed as a function of z. And so the vector form of the computation graph would just have an arrow going from vector z to vector y. And the chain rule for multivariate derivatives, chain rule for partial derivatives, says that the error signal for zj is the sum over all of the children in the computation graph, the error signal for yk times the partial derivative with respect to zj. And if you write this in vector form, what this is exactly is it's the Jacobian for that layer transpose times the output error signal. So basically, each step of backprop is multiplying by the transpose of the Jacobian matrix for that layer of the network. And so this is the Jacobian matrix of y with respect to z, so it's the Jacobian for a single layer of the network. And so for instance, if you have a linear operation, so z equals w times x for some matrix w, then the Jacobian of that operation is just w. And so the backprop operation will be J transpose times Z bar, which is just W transpose times Z bar. A slightly more interesting example is if you have an element-wise operation. Like let's say you take the element-wise exp of the activations in the previous layer. The Jacobian of that operation is a diagonal matrix because you're operating on one element at a time. So the diagonal entries are the derivatives of the activation function, which is just exp of zj. And so when you multiply by the Jacobian, then that's essentially, well, the diagonal matrix times a vector is just an element-wise product. And so this is an example of how, even though conceptually what we're doing is multiplying by individual layer Jacobians, we never want to construct those Jacobians explicitly, right? There's no reason to construct this diagonal matrix. You'd rather just define an operation to multiply by it. And so if you look at how automatic differentiation packages like TensorFlow are implemented, they, for each of the operations they define, they also define a way of backpropping through it, which is basically a vector Jacobian product. Right, so you just need to define one of these for all the operations that the framework supports. There's actually a really neat package called AutoGrad, which is a very slimmed down implementation of an autodiff system in about 150 lines of Python code. So I definitely encourage you to check that out if you're interested in how these things actually work. All right, and so one kind of special case of this view of backprop is if you have, if the relationship between two nodes in the network just includes one pathway, then the Jacobian, right, so the pathway from x to y just includes this one path. And so the Jacobian for y with respect to x is just a product of the Jacobians of the individual layers leading up to it. And so that's the case that we'll be dealing with in the research talk today. And so essentially you have the Jacobian for the whole network. It's just the product of the Jacobians of the individual layers. And so what backprop is doing is it just multiplies by JYX transpose. So using this factorization, it just multiplies in sequence by JYH transpose, JHZ transpose, JZX transpose. So all it's doing is essentially using that factorization. All right, so that's how the Jacobian decomposes into layer-wise Jacobians. And it looks like I'll only have time to talk about one more topic, and that's what the Jacobian tells us about how the curvature affects neural net optimization. And so the relevant quantity here is the Hessian matrix. So that's the matrix that tells you how much the cost function curves upwards in various directions. So the quadratic form defined by the Hessian matrix tells you the local curvature. And I mean, it's a symmetric matrix because the partial derivatives are symmetric. And what this means for optimization is that if you have a function with ill-conditioned curvature, which means that it curves really quickly in one direction and very slowly in another direction, then if you run gradient descent with a fixed learning rate, it'll basically bounce around really quickly in the directions of high curvature and get stuck in the directions of low curvature. And so if the different eigenvalues of the Hessian are very different from one another, then that makes it much harder for optimization. So that's ill-conditioned curvature. And we can understand the Hessian by looking at what's called the Gauss-Newton approximation. Okay, and here we're looking at a single training example. So the Hessian of the full cost function will be a sum of this thing over all of the training examples. But basically, we're approximating the Hessian with respect to the optimization parameters as the Jacobian y theta. So this is the Jacobian of the network outputs with respect to the parameters. That's different from what we've been looking at so far. We've been looking at the Jacobian with respect to the inputs. So they're related. Basically, we approximate the Hessian as j y theta transpose times hy, the Hessian with respect to the outputs of the network. So if it's a least squares regression problem, that's just the Hessian of the squared error, which is the identity matrix, then times the Jacobian again. Right? And this is basically approximating the network's computation as linear. So it's a linearized approximation to the network. And this is regarded as a fairly good approximation in deep learning. And so if you're applying second order optimization to a neural net, you're probably using this approximation to the Hessian. So we're ignoring the second derivatives of the network function itself. And the intuition this provides is that, right, so why does the cost function curve rapidly in some directions and slowly in others? Well, we can take, so V is an arbitrary vector, and we want to evaluate the quadratic form. So V transpose HV, using this approximation, we can write that as the Jacobian times V transpose times the output layer Hessian times the Jacobian times V, right? So the Jacobian times V basically says how sensitive are the network's outputs to that direction in parameter space. And so the reason you have high curvature in some direction is that moving in that direction changes the network's outputs a lot. Moving in some other direction might not change them very much.
So if that's exact, then why is it only approximate?
Oh, sorry, this should be approximate. I'm sorry, it's a typo.
Okay. Is there some version of this that makes it, is there some tweak to this idea that makes it exact, or is it, what is the approximation based on?
So the Hessian can be basically written as a sum of two terms. So one term, which is this one, involves the first derivatives of the network function and the second derivatives of the output layer. and the other term involves the second derivatives of the network function and the first derivatives of the outputs. And I mean, there's sort of one justification for doing that, which is that if you're in the setting, so if the true function is realizable, and there's no label noise, then you can match all of the training labels exactly. So the second term will involve the first derivatives of the cost function, which vanish when you're at the optimal solution. And so basically, close to the optimum, this approximation will actually be accurate and it'll behave just like exact Newton's method. If you have label noise, or the true function is not realizable, then that term will not vanish near the correct solution. But it still seems to work well in practice anyway.
But it's exact at the optimum.
It's exact at the optimum if the true function is realizable and there's no label noise. And so the upshot is that if we'd like to make the Hessian well-conditioned, then we want to make the Jacobian well-conditioned. So that's the Jacobian of the outputs with respect to the parameters of the model. And it turns out that that Jacobian can also be written in terms of Jacobians of individual layers. And it's kind of more clunky in terms of the notation, but it still works out. And so if you, right, so for purposes of optimization, it's advantageous for the Jacobians of individual layers to be well-conditioned. And so particularly we want the singular values for each layer's Jacobian to be close to equal. And so this is one motivation behind a trick, basically orthogonal initialization. So rather than sampling the weight matrices as IAD Gaussians for all the entries, you can sample them as orthogonal matrices, and the Jacobian for the linear part will then be unitary. So all the singular values will be unit norm. All the singular values will be 1. Right, so that's one perspective on why Jacobians are useful for optimization. Finishing up with the optimization story, I'll just mention one thing, which is that the Jacobian, in some settings, tells you a lot more about optimization than you might think. So in particular, as you make a network wider, then it's possible for it to fit the training set while moving a much smaller distance than the initialization in terms of L2 distance in the weight space. And if it only moves a small distance from the initialization, then the first-order Taylor approximation around the initialization could actually remain accurate throughout training. So it's not true for small networks. It's not true for narrow networks, but it actually seems to hold surprisingly well for wide networks. And so there is this really neat empirical paper by some people at Google that looked at the training of very wide convnets. So there are a few things that are kind of atypical about the training regime. You had to use very wide networks, very small learning rates, and full batch training. So it's not really a practical training regime, and it doesn't do quite as well as how we normally train these networks. But if you're in that regime, then throughout training, everything is very well approximated by the first-order Taylor approximation around the initialization. So this plot shows the values of different outputs of the network. The solid curve is if you train the actual network. The dashed one is if you train the linearized approximation. And they match almost perfectly. And you can look at the training and test loss as a function of time, and those match almost perfectly. So it's kind of surprising how powerful this approximation is. And in the limit of infinite width, then the dynamics are exactly linear. And you can actually analyze them in terms of an object called the neural tangent kernel. And so that's become a really big thing in the theory of deep learning over the last couple of years. And so you can get a lot of insight into optimization and generalization effects by looking at this infinite width limit. Okay, so I'll very quickly cover exploding and vanishing gradients then. And so this is a problem that comes up if you're trying to train very deep networks or recurrent neural networks, which are typically unrolled for a lot of time steps. And the problem is basically, since I've already introduced the Jacobians, I'll remind you that the layer-wise Jacobians multiply to give you the Jacobian for the whole network. So this is the Jacobian from the hidden states at time step 1 to the hidden states at time step t. So all these Jacobians multiply. So you're multiplying lots and lots of matrices together. And so if the matrices are all small, then the Jacobian will vanish. And so the backpropagated gradients, therefore, will also vanish. If the matrices have large singular values, then it's possible that the gradients will explode. And so if you want to train a very deep network, or if you train an RNN for many time steps, then you have to somehow deal with this problem. It's not a problem for the forward pass of the neural net, because there's usually some sort of operation that prevents things from blowing up. So either some sort of nonlinearity that compresses the activations to be in a particular range, or some sort of normalization scheme like batch norm. There's something that keeps things from blowing up, but the backwards pass is always linear. So you're just multiplying lots of Jacobian matrices together, and so unless these matrices are very nice, things could explode or vanish. And so that's what happens mechanistically in terms of the gradient computations. We can also think about it conceptually in terms of what the network is actually computing. So the Jacobian just means, right, how much does ht change when you change h1. And if you think about an RNN, it's basically, so if the weights are the same in every layer, right, for every time step, then each time step computes some function of the current input and the previous hidden activations. And you're just iterating the function lots of times. And iterating a function, even a very simple one, can produce some fairly complicated behavior. So here's sort of a classic example. If you iterate the simple function 3.5 times x times 1 minus x, it's just a quadratic function. But if you iterate it lots of times, then you get chaotic behavior. And so the exploding gradients happen when the output is just unstable with respect to the input. So in kind of chaotic regions, things explode, and in flat regions, things vanish. So how do we deal with this problem? So one of the big advances in classification convnets was the residual network architecture. That's based on residual connections. It's a very simple idea. It says that the output of the layer is some nonlinear function of the input, then we also add the original input to it. And you can represent that as a skip connection. So the input directly feeds into the output. And mechanistically, in terms of the gradient computation, that means the Jacobian of this layer is the identity plus the Jacobian of the function f. And so as long as you keep this Jacobian small, then the Jacobian for the layer will be close to the identity, and it'll be well conditioned. So it's at least possible to, there's some like easy way to represent things that are well conditioned. And in terms of what the network is actually computing, this makes it easy to represent, so what's sort of the default thing that a layer in a neural net could do, right? If there's nothing interesting for it to do, it could just like pass the information through without modifying it. And having the skip connections makes it easy to do that. So that's the residual architecture. For RNNs, there are two ideas that became popular around the same time. So there's the long-term, short-term memory architecture and gated recurrent units. And so one of the things that's useful about them is that they make it easy to represent the identity operation, which is just a good default thing for the layers to compute. And And so this sort of analysis of the Jacobians of each layer gives some insight into how to initialize the network. So traditionally, we just initialize the network using independently sampled Gaussian distributions for each of the entries. But if you have a weight matrix that's kind of approximately square with IED Gaussian entries, then it'll have a very broad distribution of singular values. And that's not good from the standpoint of propagating information through the network. And so there have been a bunch of interesting papers recently that looked at this question of how to initialize the networks in order to keep the singular values of the Jacobians close to 1. There's a property called dynamical isometry. It's not sufficient to only orthogonalize the weight matrices, because you also have nonlinear activation functions to worry about. But they've found ways to do this in various settings. And if you initialize it just right, you can actually train 10,000 layer networks with things like logistic activation functions, which are generally considered to be really hard to train. And they can do that without using all our other modern tricks like residual connections and batch norm. Right, so that's it for the talk. And so just to remind you, we've talked about Lipschitzcontinuity, why it's useful, and how it's connected to the Jacobian of the network. And we looked at how you can decompose the Jacobian into layer-wise Jacobians, and how that's basically what backprop is doing anyway. And we looked a bit at how the Jacobians of the network relate to neural net optimization, and why it's advantageous to keep the Jacobians well-conditioned. So hope that sets up the relevant background for James and Jem to talk about Lipschitz-constrained architectures.
Yeah, it's really fantastic to be here today to talk about one of the most interesting research projects that I've ever been a part of. James, Lucas, and I have contributed equally to this project, and needless to say, none of this would have been possible without the close guidance of Roger. So with that said, let's begin with our research objective. So our goal is to train neural networks with a strict Lipschitz constraint while making sure that they maintain as much expressive power as possible. So Roger already went through this in the primer, but I'll quickly summarize once again. The Lipschitz constraint basically means if you change the input to a function a little bit, the corresponding change in the output must not exceed k times the sort of norm of change in the input. And this takes an even more convenient form locally, where the gradient norm must not exceed k. Why do we care about training Lipschitz neural networks? Roger also went over this. I'll quickly summarize. Because there are many problems actually in machine learning where having control over the Lipschitz constant is really useful, such as training robust classifiers, comparing probability distributions using the Wasserstein distance, comparing generalization bounds. It comes up in reinforcement learning where you also use it to bound certain types of errors. So you can think of Lipschitz neural networks as basically an important part of our sort of expanding deep learning toolbox. Let's get a bit more specific about our research goals. So we would like to come up with a method, an algorithm, an architecture, something that will let us train networks that are constrained enough that they never violate a given k-Lipschitz constraint. We don't want to even tolerate k plus 0.001. But we want our networks to be expressive enough to be able to actually approximate any k-Lipschitz function. So just want to emphasize that the actual challenge here is the second one, because f of x equals 0 is k-Lipschitz, but it cannot represent anything. So we want really this expressivity. There are pretty much two ways we could go about doing this. We could either try to enforce the constraint softly, maybe via some regularization term in the loss, and then after training, we can verify the Lipschitz constant, or we could actually come up with an architecture, a Lipschitz constraint architecture, which always will obey the k-Lipschitz constraint. In this work, we focus on the latter one, mainly because there are problems where we actually really care about having that strict, precise control over the Lipschitz constant, the explicit control, like training robust classifiers in the Wasserstein distance. and also like getting a good estimate of the Lipschitz constant of neural networks is on its own a very challenging task itself. So by the end of this talk, James and I will have introduced a new class of expressive Lipschitz architectures, and we will have sort of evaluated their performance on a number of sort of practical tasks. All right. Probably the first step most of us would take when trying to tackle this challenge would be to exploit the composition property of Lipschitz functions. So as Roger said, if you have two functions f and g that are one Lipschitz, so the Lipschitz constant is 1, f of g is going to remain 1 Lipschitz. So if you have a fully connected network that has 1 Lipschitz linear layers and 1 Lipschitz activation functions, we are guaranteed that the whole thing is going to be 1 Lipschitz. And if we want a k Lipschitz constraint, we can just scale the output by k, and we have a k Lipschitz constraint. So the challenge really becomes, how do we enforce the Lipschitz constraint on the linear layers and the activation functions? So let's start with the linear layers. If you're operating in sort of Euclidean norm, like L2 norm, it basically says the weight matrix of the linear layer is not allowed to expand the vector it's operating on in size. It is allowed to shrink it, rotate it, or flip it, but it cannot expand it. And in L infinity norm, it basically corresponds to that the geometric intuition is if you take the rows of the weight matrix and sort of plot it, they should all lie in this sort of multidimensional diamond-shaped region. I should also specify that for the L2 norm, the condition I've described geometrically corresponds to having the largest singular value less than or equal to 1. We'll talk a lot more about how to actually algorithmically do these later in the talk, but for now it suffices to say that this has been studied very well in literature before, and there exists a cheap, fast, convenient ways of achieving both of them. And it's even easier for activation functions, because almost all of the activations functions we use today commonly can be trivially scaled so that the slope doesn't exceed 1 anywhere. So is this what it takes? In terms of the constraint, yes. These methods will definitely give us a strict k-Lipschitz constraint. But in terms of expressiveness, we have to check. We have to confirm, or maybe show, we have to confirm that either that they are expressive enough or show counterexamples that they have some limitations. Let's start simple. Take a sort of 3-layer fully connected neural network and try to train it to approximate the absolute value function. So absolute value function is 1 Lipschitz, right? Because it has a slope of 1 everywhere. So let's take the linear layers for granted now, and let's just pick 10h, like a common activation function. This is what you get when you train with 10h. So it's not the absolute value, obviously. Maybe ReLU will do better, because it's like piecewise linear. It doesn't really work as well. So something is going on. It could be an optimization issue. Maybe our optimizers cannot really find a good solution. Or it could be a problem with the architecture itself. And it turns out that it's actually an architectural limitation. And this becomes quite obvious if you plot a certain graph. It becomes immediately obvious why. So this plot here shows the norm of the gradients that are being backpropagated through the network from the output towards the input. So each operation is 1 Lipschitz, right? That was our sort of design principle. So both in the forward pass and in the backwards pass, they're not allowed to expand the size of the vector they're operating on. So the gradient norm, if we start there, cannot ever exceed unity. Does that make sense? But the 1 Lipschitz constraint allows us to shrink the gradient norm. And if we actually plot this graph for the networks we train, we observe this phenomena. The gradients norm starts and go on shrinking. Absolute value has a slope of 1 everywhere. So the only way really to be able to approximate absolute value is to have the gradient norm stay at unity throughout the network. And I'll just pose a quick rhetorical question. Can you think of a way in which a ReLU network with 1 Lipschitz constraint have a gradient norm of 1? The answer turns out to be yes, but only if all the inputs to the ReLUs are positive, in which case the ReLU is no longer a nonlinearity. So it's just a linear network we end up with. So this is the problem. So we have, yes?
Could that be solved by k being bigger than 1?
K, yes, but then then you can actually, OK, let's say you want a 1 Lipschitz constraint. You can maybe choose k to be 2 to approximate absolute value, but you're no longer guaranteed to have that 1 Lipschitz constraint. With the same architecture, you can actually get a 2 Lipschitz network. So we really care about that strict control. So we want to first constrain the architecture and then train it to actually achieve that Lipschitz constant. Does that make sense? All right, so this is the problem, gradient norm shrinkage or gradient norm attenuation. So we have a slightly more general theorem to show the problem about the absolute value, about the activation functions. This is an informal statement. So if you take a neural network like the one I've talked about before and use 1 Lipschitz element-wise and monotonically increasing activation functions, ReLU, 10H, LU, like most of what we use today fall into this category, then we can show that if the function this network is computing has a gradient norm of 1 almost everywhere, then it must be linear. In other words, if it's representing a nonlinear function, there's no way it's going to have a gradient norm of 1 everywhere. So this architecture isn't expressive enough. This is another sort of chart that shows that this tension between nonlinearity and norm preservation happens in practice as well. You take a similar network and train it on MNIST classification. This is a relatively complicated figure. I'll just try to convey the main message of it. We're trying to capture the tendency of the neural network to keep its ReL units active, because that's the only way it's gonna push its gradient norm up. If it's using a lot of ReL networks, if it's keeping a lot of ReL units off, then it's losing a lot of norm. And we see that if we train a 0.1 Lipschitz neural network, around on the very right slice of the graph, you see that around 8%, I think, of ReL units are always active. So they're not even contributing to the nonlinear processing at all. And we see that as we increase the Lipschitz constant, the behavior, the tendency of keeping the ReL units active gets closer and closer to the standard networks with no constraints on them. So this happens in practice as well. So these are strong negative results. So maybe there just isn't a way to have this strict Lipschitz architecture and let it be expressive. But it turns out that there actually is a way to get around this problem. If the problem was that the norms were necessarily shrinking, can we come up with methods that will actually keep the norm the same? Like sort of preserve the norm. So the idea is we would like to come up with linear layers and activation functions that are gradient norm preserving. As a sort of sneak peek to our results, if you do this, you actually can perfectly approximate absolute value function with 2 neurons. So I'll now explain how to actually get these gradient norm preserving units. Let's start with the activation function. What we use here is an activation function we call group sort. What group sort does is it takes the pre-activation and it sorts them. You can sort all of them. You can sort all the units. You can sort them in pairs, or you can sort them in groups of 5. And here you can see the left 5 units are sort of considered and they're sort of passed on, sorted. So this is our activation function. And let's talk about why this is even an activation function and the properties of it. It's continuous, check. It's nonlinear because you can think of sorting as applying a permutation on the inputs. And basically the permutation matrix itself depends on the order of the inputs. So it's a nonlinear operation, check. It's differentiable also because of the sort of permutation viewpoint. In the backwards pass, the Jacobian you compute will also be a permutation matrix, check. And most importantly, it is gradient norm preserving. Because all we're doing, both in the forward pass and in the backward pass, are literally just shuffling the units in a sort of deterministic way. And shuffling the units among each other will preserve the norm in all norms. So this activation satisfies all the properties that we're looking for. Just a special case, if you're sorting pairs of units, we call that max-min, like finding the max of 2 and the min of 2. And it was pointed out to us that this activation in this form was actually proposed 4 years earlier by another group doing research in RNNs. So you might wonder whether the group size matters. It turns out that in terms of expressive power, the answer is no, as long as we allow our networks to have varying depths. And the reason for that is, basically you can implement like a parallelized bubble sort with a couple layers to sort the whole thing, the whole pre-activations. Or if the activation sorts the whole thing, you can pick the neural network, pick the weights of the previous matrix so that only the pairs of units are comparable in size. So a single full sort operation can also represent max-min, which is the pairwise group sort. So in terms of expressiveness, there's no difference. But in terms of optimization, the answer is yes. We found that it's in practical cases, it's easier to optimize the maximize max-min networks. But I just also want to emphasize that it does work if you sort the whole thing. Like we tried changing a fully connected network to the MNIST classification, and we had a hidden layer of, it was 1,000, right? 1,000 hidden units, and also added like 50% dropout on top of it. So we have a network that takes some activations, like sorts all of them, and like drops 50% of them randomly. And this actually ends up getting close to 95% accuracy on the MNIST test set. Like, it's terrible for MNIST, but it's kind of like interesting that it even works. So how does group sort lead to other activations? You can show that you can recover ReLU, leaky ReLU, concatenator ReLU, and max out pretty much many of the common piecewise linear activation functions we care about, while also maintaining the one Lipschitz constraint on the weight matrices. But the reverse is not true. Using ReLU, you cannot go back to group sort. So group sort is more expressive than these activation functions in the Lipschitz setting. And also importantly, you can represent the absolute value function using group sort, which lets you fold the space of like the hidden layers along arbitrary hyperplanes. I don't want to dwell too much on this, but I'll just say that the idea of approximating complicated functions using a series of folding operations has been studied in literature. So this gives us some insights into how we expect group source network to operate and solve problems. The last slide on group sort just gives some insight on how it actually works from a different angle. On the left-hand side, we have the pre-activations of 4 units and how they change as we change the input to the neural network. Like the blue one is 1 unit, a red one is 1 unit. And as we sort them, basically, the first unit becomes the top one, like the U-shaped one. The second one becomes the red one, the middle V, and so on. So this is just to give some intuition on how group sort works. Okay, on to linear transformations, norm-preserving linear transformations. James will talk much more in depth about this. I'll just make 2 quick remarks. It suffices to make sure that our linear transformations are orthogonal for them to be norm-preserving. And what this really means geometrically is they're not allowed to neither expand nor shrink the size of the vectors they operate on, but they're allowed to rotate or flip. So then the problem really becomes, how can we pick or design matrix projection algorithms that take unconstrained weight matrices and projects them on the space or a manifold of orthogonal matrices or L-infinity constrained matrices. And James will talk much more about that in the latter part of the talk. Okay, so these are the tools we want to use in our network. So did this idea of norm preservation gain us anything? So we need a way to quantitatively evaluate how expressive our networks are. And here, actually, the Wasserstein distance comes to our rescue, or specifically the dual form of Wasserstein distance. If we come up with two probability distributions whose Wasserstein distance we can analytically compute, then on the right-hand side, basically what the problem is saying is find the Lipschitz function that will assign as high values to samples from one distribution and as low values to the other one, while obeying the Lipschitz property. So if our network is expressive enough, it will be able to find the optimal one. If it's not expressive enough, it's going to fail to give us the optimal Wasserstein distance, the correct Wasserstein distance, and we'll be able to even visualize this function and see why it failed. So this is a very convenient way of evaluating Lipschitz expressiveness. I'll give a very quick example of how this works. Is there a board marker? Oh, right here. Yeah. Okay. So let's say one of the distributions is just like a Dirac delta at the origin, and the other one are like half here at -1 and half here. So you'd like to come up with a Lipschitz function that assigns, say, as low values as possible to here, to the samples from this distribution, which are always 0, and as high values as possible to this and this. So what's the answer to this? It would be the absolute value, right? And if you sort of, we can also quickly analytically compute what the optimal Wasserstein distance should be, which in this case turns out to be 1. I hope this is visible. The board marker is almost done. Right. So let's start with a visual example. So in this case, we picked the probability distributions P1 and P2 such that the optimal Lipschitz function looks like 3 consecutive cones with gradient of with a slope of 1 everywhere. So when we train norm-preserving and non-norm-preserving architectures, we see that the group sort architecture is able to almost perfectly approximate the target, where other activations like max out and ReLU cannot get close. By the way, I forgot to mention that all the estimates of Wasserstein distance are lower bound, so the higher is better. And in this case, we see that the estimates we get with group sort are almost exactly the same with the correct one, but the ReLU and max out ones fall short. Using the same evaluation strategy, we can increase the problem dimensionality and test how our methods work for higher dimensions. And we basically get the same picture here. So in this table, we're trying to fit higher dimensional absolute values and see how we do. And we see that somehow sorting the whole activations is strangely suited for this problem. It gets perfect performance for all dimensionalities. And overall, we see that norm-preserving activation functions give us significantly closer, tighter lower bounds of the Wasserstein distance. So they're more expressive. This is another figure that I really like. In this case, we designed a 10 Lipschitz fully connected neural network and trained it to do MNIST classification. If we pick ReLU as our activation function, even though by construction the network has the capacity to represent 10 Lipschitz functions, we actually end up getting practically Lipschitz constants around 7 and 7.5 around the training data. So the ReLU networks aren't able to utilize the Lipschitz capacity they're given. But if you use norm-preserving architectures, like group sort architectures, you get like precisely 10. So we're able to match the Lipschitz constant that we set out to achieve in the beginning. And if you plot the singular a histogram of all of the singular values of the input-output Jacobian, we see that still we're pretty close to 10, which I guess in reference to the last part of Roger's talk, this shows that the input-output mappings we learn are very well conditioned, and they satisfy the dynamical isometry property not only in the dynamical isometry property throughout training as well. And I guess like as a side effect of this approach, we also get around vanishing and exploiting gradients for free. So in the previous slides, we used Wasserstein distance to evaluate our architectures. Can we actually do the reverse? Like, can we actually try to compute the Wasserstein distance using our methods? So let's say we have a set of two high-dimensional, two sets with high-dimensional objects, like images, and we basically train our networks to compute the dual form Wasserstein distance. And all across the board, we see that the group sort networks with norm-preserving linear transformations get significantly tighter lower bands on the Wasserstein distance, so they get better estimates. I haven't explained what Bjork is yet, which is the linear norm-preserving operation. And just a remark, currently, if you look at literature on how people normally solve these problems, solve this problem, the most common approach is ReLU with spectral normalization, which is by far the weakest option that we have in this experimental setup.
So what are the two distributions here?
Oh, so in this case, okay, we have two sets of images. In this case, it happens to be, I think, MNIST, the empirical distribution of MNIST, and a GAN-generated MNIST. So it's kind of like the discriminator of a Wasserstein GAN. Does that make sense? Basically, that's basically for us to be able to concretely get a sort of high-dimensional problem. It doesn't really matter what the distributions are. So I guess the main point is, yeah, that's your question? So this one is samples from MNIST.
I'm not sure what task you tried to do that the table's referring to.
Oh, we tried to optimize the dual form Wasserstein distance objective. So basically find a one Lipschitz function that assigns as high values to samples from one distribution and as low values to the other one. So higher is better in this case. Yeah. Actually, that is a good, I guess, a good way to move on to the next slide, which is we can actually use our methods to train Wasserstein GANs as well. But evaluating GANs is a very difficult challenge, so we leave that for future work. So if there's one takeaway that I would really want to emphasize from my part of the talk, it would be that it's actually possible that to design a K-Lipschitz constraint architecture, train it, and in practice actually get that specific K-Lipschitz constraint that you wanted to get. So we can have a really strict control over the Lipschitz constant of the networks we're training. And the real win for us would be if we could show that our methods are universal approximators of Lipschitz functions, which James will be talking about shortly. So that's my part. Any questions that I can answer? Yes?
Just talk a little bit more about the intuition, like why it fails to learn the absolute function.
Okay. So let's pick ReLU as an activation function. So where were you? Oh, sorry. So absolute value has a slope of 1 everywhere, right? So if you want to compute the input-output Jacobian will have a norm of 1. And each of our units, the computational units, activation functions, linear transformations, are 1 Lipschitz too. So their Jacobian, the norm of their Jacobian will also be bounded. So in Roger's part of the talk, we saw that input-output Jacobian can be written as a sort of product of layer-wise Jacobians. So as you sort of matrix multiplicate, so as you multiply them, you're not going to be able to increase the norm ever in the backwards pass, but you're allowed to shrink that. In absolute value, we want to keep that around unity, but if we don't have the right tools for that, they will necessarily lose norm as they go backwards. So think of ReLU, like the only way that a ReLU activation becomes norm preserving is all the inputs to the ReLU units are positive. So in that case, ReLU isn't like ReLU is just identity transformation. So it's not really nonlinear anymore. So it kind of defeats the purpose of having the activation function from the beginning. I hope that explains.
I think we should move the rest of the questions to discussion at 11 to make sure James has a chance to do his part.
Oh, great, thank you. Yeah. Is the microphone on? Yeah, sounds like it. Okay, great, thanks. Yeah, so I'm James Lucas, another PhD student in Rogers Group at the University of Toronto. I just want to reiterate again how excited I am to be here and sort of talk about this work with all of you, and I'm really keen to get feedback in the discussion section afterwards to hear your thoughts on this. In my section, I'm going to focus on universal approximation. I'm going to walk through sort of a simple proof of, a simplified proof of our architecture as universal approximators, and I'll say a bit more about what that means. And also talk a little bit more about some applications and look at some empirical results. So just to recap what Jem covered in his talk, he highlighted that our goal here is to build these expressive Lipschitz-constrained architectures, where we really want to have both expressive and constrained together, and there's some tension appearing between these two things. We saw that the way to solve this problem is via this property Jem introduced called gradient norm preservation, and Jem introduced an activation function group sort, which allows us to get gradient norm preservation, and also pointed out that we can recover norm-preserving linear transformations. And ultimately, combining things together gives us gains in expressive power. So in this section, I'm first going to talk a little bit more about these norm-preserving linear transformations. In particular, I'll point out how we can achieve orthogonal linear layers in practice. And then I'll prove that our Lipschitz neural networks are universal approximators of Lipschitz functions. There's some subtleties there that I'm going to talk about a little bit when we reach that section. And finally, I'll talk about some of the empirical results that we studied in this work, some actual practical applications for adversarial robustness. So as Jem pointed out, we require norm-preserving linear transformations for both L2 and L-infinity norm. So several algorithms exist for both of these. It turns out that existing algorithms for L-infinity projections work well in our setting without much additional work. So I'm not going to spend too much time speaking about those. But there was this paper that was very helpful for us by Condat in 2016, where he wrote down some nice differentiable algorithms to do this. I won't speak about those too much, but it's a nice read if you are interested. Unfortunately, it turns out doing this for L2 norm is a little bit tougher. I might ask, why is that? Optimization over orthogonal matrices, which is really the problem we're trying to solve, is a well-studied problem. People have been looking at it for a couple decades or more now. But neural networks really stretch the limit of these tools. The weight matrices we're optimizing over might be 1,000 by 1,000 matrices, and we'll have several of them in our neural network due to all the layers. And this problem gets harder as the network gets deeper. So ultimately, this sort of standard tools applied to this setting are difficult to translate into this, into these neural network problem settings. So the tool we choose to solve this comes from a paper from Bjork and Bowie back in 1971, and we sort of coined the name Bjork orthonormalization just to give the name to their algorithm. But this algorithm on the label is pretty simple. We take a matrix W, a weight matrix. We apply this algorithm that I'll write down in a moment, and the algorithm will spit out the closest orthogonal matrix to W. But it's worth taking a moment just to write down what we mean by the closest orthogonal matrix. So if I have a weight matrix W, I can write its singular value decomposition as some orthogonal matrix U times some singular matrix, and some diagonal matrix S, and some orthogonal matrix V transpose. And if I take Bjork of W, all right, let's actually line here. Just to reiterate what this S is, if we have an arbitrary sort of unconstrained matrix, then assuming this thing is square for now and has all positive singular values for simplicity, this matrix is going to be a diagonal with entries S1, S2, down to, say, Sn, where these S values are unconstrained. They could be any positive values. If I apply the Bjork orthonormalization scheme, this transforms this matrix in the following way. So I'm going to have the same matrix U here. I'm going to have a matrix with all ones along the diagonal, and then the same V transpose. So this is also known as the polar, this also appears in the polar decomposition of the matrix, and it turns out this thing is sort of the closest orthogonal matrix to the original W under the Frobenius norm. So there's like some nice properties here, but really this Bjork algorithm is projecting W to some reasonable orthogonal matrix that represents the same transformation. It captures like the rotation and flipping effects. Okay, so what does the algorithm actually do to achieve this? So the algorithm computes the following iterative updates. I'm going to repeatedly apply this transformation. I'm going to take my weight matrix WK, and I'm going to compute 3 over 2 WK minus a half this matrix product. And I'm going to repeat this over and over again. I'll point out that this is sort of a special case of the Bjork algorithm, but it's the one that we mostly focus on, so I'll just stick with this for simplicity. But note importantly that this algorithm is fully differentiable. So if I run this thing for t steps and I get some wt out at the end, I can take the derivative of wt with respect to my original w0 because it just computed a linear map of these matrices. So this is a nice property to have when we care about using backpropagation to optimize things. Which leads me on to my next slide, which is how do I actually use this algorithm? So this gives me a way to take a weight matrix and compute an orthogonal representation of that matrix, but how do I use that in practice? Well, once again, I'll move to the board. So I wrote down a couple options here. We could think about doing this after the gradient update, or I said during the forward pass. Let's see, that's a bit tricky. Okay, so I'm going to sort of use a simplified representation of the space we care about, which is to say we really care about optimizing on some sort of smooth surface of. So in this case, this represents the orthogonal matrices, which is a smooth manifold. If that language doesn't make sense to you, don't worry. It's just to say that we want to use weight matrices in our network that sort of lie on this surface. So let's say I initialize my weights. I get some W1 that initially lies on this surface. The first option I wrote down here is doing this after the gradient update. So what I mean by that is I'm going to use this weight matrix W1 in my neural network. I'm going to compute gradients, and I'm going to update the weight matrix. But there's no guarantee that this, after the update, the weight matrix remains orthogonal. So I'm going to move some distance away from the orthogonal manifold. The new weights are no longer orthogonal after the gradient update. I can then apply the Bjork algorithm at this point to sort of project me back. Let's write W2. I can then apply the Bjork algorithm to project me back onto this manifold and then reuse these weights again in the next forward pass. And I can sort of repeat this procedure like over and over again during optimization. This way, we ensure that every time we run the forward pass for our algorithm, we're always using an orthogonal matrix. And so we have this Lipschitz constraint property we care about. And then we sort of fix the errors incurred by the gradient update at each step by projecting back. So unfortunately, while this is a very sensible approach, we found that this had some sort of unexpected stability issues when we tried to do this in general. And these are things we're sort of thinking hard about now correcting, because we don't understand a strong reason why this shouldn't work, but we have some ideas. So instead, we utilize a slightly different approach, which is, suppose instead I just have some unconstrained weight matrices. What I could think of doing instead is I could apply the Bjork algorithm on these unconstrained weights and sort of project them down to this space. And then I can compute my gradient, sort of backpropagating through the Bjork algorithm, like I said I could before, and I'll get some update for my unconstrained matrices here. So now on this, like in memory, I'm just keeping track of these unconstrained weight matrices in memory, and then each time I run the forward pass, I do this Bjork algorithm, and then backpropagate through everything to update the unconstrained weights, and repeat this like at each time step instead. So both of these methods guarantee that in my forward pass, I'm always using an orthogonal matrix. I have a Lipschitz neural network, but there's sort of some trade-offs in terms of computational complexity and other things that I won't go into too much right now. So the sort of core summary of this is that we choose to do this during the forward pass, backpropagating through the algorithm. So we adopt the approach where we have some unconstrained weights, and at each step of the algorithm, we're going to project these to the orthogonal matrices using the Bjork algorithm, and then backpropagate through this procedure. I'm happy to talk offline about more of the intricacies, exactly why we choose to do that, but the summary is that we found it works well. So we should also ask, when does this algorithm converge? What conditions do we need on the matrices such that the Bjork procedure can indeed find this orthogonal matrix? It turns out we just need a bound on the largest singular value. That's all that's required for this matrix to converge. And we can also use a sort of fortunate consequence of the Bjork algorithm, which is that the output does not depend on the scale of the input. By which I mean the way that the Bjork algorithm finds the closed orthogonal matrix is just by setting these singular values to be equal to 1 everywhere. If I multiply the singular values by some constant, it doesn't change the output. So I can just pick a constant such that my largest singular value is lower than the bound I need, and then I'll guarantee convergence. There's some sort of effects on convergence speed and other things, but ultimately we can sort of abuse that to use cheap approximations like power iteration to make sure this thing will always converge. And finally, we should address sort of the elephant in the room. Isn't this very expensive? For those of you that were paying attention, I wrote down this algorithm that's iterative, that does a bunch of matrix-matrix multiplications. That's not really something you want to see in numerical computation. So the answer is yes, this is expensive. So one sort of saving grace is that this algorithm can be nicely parallelized. So if we observe that in a standard neural network, during my forward pass, everything is computed sequentially. But if I'm doing this sort of projection of my unconstrained weights down, this doesn't require any data to do. So as soon as I do my gradient update, I can just kick off a bunch of parallel jobs that do this orthonormalization, so that when I start my forward pass, like everything is there ready for me. Turns out people have done this, and I think if you have access to a TPU, this basically becomes a free operation. Like, that's a lot of compute to throw at the problem, but turns out it's not actually a real bottleneck, and people have trained ImageNet classifiers using these kind of setups. There's some other sort of more, I think, enticing algorithmic improvements to be made that we're currently working on, and again, I'd be excited to speak about some of those things offline. Okay, and just to go back and ask this question, why do we choose Bjork's method? We've sort of seen a couple other things alluded to in both Roger and Jem's talk, one of which was spectral normalization, which again, I'm going to avoid sort of carefully defining, but I think Roger pointed out that it's just dividing a matrix by its largest singular value, which is computed via power iteration. So actually, it turns out for neural networks, this can be done efficiently, and it's used quite a bit, but it bounds only the largest singular value. This means that we don't guarantee norm preservation, we just guarantee the Lipschitz constraint we care about. And it turns out that having this norm preservation is really a critical property. So to sort of demonstrate this, here I'm plotting the convergence behavior during training of the Bjork method versus spectral normalization on these Wasserstein distance estimation problems. So achieving higher up on the curve is better. And I'm plotting different versions of the Bjork algorithm with varying dimensionalities in blue and the spectral normalization in the sort of red, pinky colors. So we see that Bjork is fairly insensitive to changes in dimensionality. Right? As I increase the dimensions of the problem from 4 to 256, I see just a small drop-off in performance. Whereas spectral normalization really suffers as I add more dimensions. And we sort of conjecture the reason for this is that spectral normalization is only sort of forcing the largest singular value to be close to 1. And if I add more dimensions that are required to solve the problem well, even though spectral normalization sort of has the capacity to solve the problem, the procedure sort of biases us towards solutions which aren't norm-preserving and are unable to solve these problems well. Another approach from Cisse and others is named parsable networks. And here they add a regularization term to the objective, which seems like a pretty natural thing to do. So we can just add an extra term that penalizes our weight matrices such that W transpose W is close to the identity, or they're orthogonal. It turns out actually that this recovers the Bjork algorithm I showed before with an extra degree of freedom I won't carefully specify. But actually taking the gradient of this thing is essentially the same. But in their paper, they apply this after the gradient update, and to sort of improve stability, they heavily downweight this regularization term, which when we want to heavily enforce the Lipschitz constraint is problematic, right? Because during training, it's unlikely our regularizer is actually forcing orthogonality. So there's a lot of sort of technical things going on here. In our paper, we more carefully discuss some of these things, and in general, there's like a lot of interesting subtle points, but the real summary is that empirically, Bjork's method just consistently outperformed the other approaches. And we've tried like somewhat desperately to find cheap things that would work well. Like it's not nice doing a bunch of matrix multipliers, but like the gains in performance for Bjork in terms of the actual quality of the networks we train is just much better. Okay, so something we haven't spoken about too much so far is dealing with convolutions. So far, everything has been the regime of linear, fully connected networks with just standard fully connected linear maps. Yes?
How does Bjork's method compare to just doing the SVD or a low rank SVD and then throwing away the singular values in terms of computational expense?
Right, so so in the work on the convolutions, actually we did look at some approaches doing that for convolutions. There's some subtle points that is easier to talk about offline, but but I think ultimately we found that Bjork's method worked out better for us than sort of doing differentiable SVD type things. But yeah, it's a good question, and one of the things we did explore, but there's always more exploration to be done. Okay, so to deal with convolutions, we can just observe that convolutions are really just linear maps with a special structure. So we can represent any convolution by some linear operation that's sort of sparse. So we can use the exact same approach we've spoken about so far. We just need to make sure this linear map that our convolution represents is a norm-preserving linear map. It's orthogonal. Unfortunately, it's not quite this easy. There's actually some really interesting subtleties that arise when you try to do this. So we had a paper led by Quyang Li and Samuel Huck at U of T, and I'll put their names and faces up at the end of the talk. But there they showed that the space of orthogonal convolutions actually has some very interesting topology that's really hard to optimize over. So we had to work quite hard to figure out ways to make this work well in practice. Okay, so we have all the methods needed to train these networks. Now the question is, are these the right methods? Like at this point, can we prove that the method we're using will give us expressive Lipschitz neural networks? In other words, do we have this elusive universal Lipschitz function approximation property? Yes, we do. Obviously, at this point in the talk, you should have guessed that. But first, why is this even hard? You know, neural networks are universal approximators. This is fairly well known for a few decades now. I can find a finite depth radio network that will get arbitrarily close to any continuous function. So the way these results are typically proved in the literature is by construction. So people will sort of explicitly build some network and show that we can sort of set its weights appropriately to find a function close to some continuous function. And these constructions typically break the Lipschitz constraints. So we can't just immediately take these constructions and apply them to our Lipschitz networks because our weights will violate this norm-preserving property we require. So let's look at that a bit more carefully. I mentioned ReLU networks. It turns out two-layer ReLU networks with sufficient width can approximate any continuous real-valued function. So you might ask, well, maybe a simple fix to that then is I take my universal approximator for these functions and I just divide the weights by their spectral norm. Right, this will give me now one Lipschitz function, and it's a universal approximator for continuous functions. But sort of counterintuitively, we've shown that this won't be a universal approximator for all Lipschitz functions. The example Jem gave, or the theorem that Jem showed, said that we can't represent absolute value with ReLU functions if we have these spectral norm constraints on the weight matrices. So it turns out like we're not the first to point out these sort of negative results. For example, there's a paper from Huster and others at Prospector Labs where they showed some negative results for infinity norm Lipschitz networks, but we do provide the first positive result, saying that we can find Lipschitz networks that are universal approximators. So what does that look like? Here's an informal statement of that theorem. So we're going to let LNP, just fancy notation for a set of neural networks, denote the class of fully connected networks whose weight matrices satisfy some infinity norm constraint, and we'll use maximum activation as a special case of our general group sort activation function. It then turns out that we can find a network in this class of networks which is arbitrarily close to any one Lipschitz function. So quick sneaky bait and switch here. We're using infinity norm constraints on the weights. We can actually be a bit more general and use mixed matrix norms, but here we're sort of shifting away from orthogonal weight matrices for a moment to look at these sort of maximum row sum constraints that we've seen previously in this presentation.
Is there a layer width, like is there depth or width constraint on?
Yes, there is, which I've excluded here, but I'll talk about in just a couple slides. Yeah. Okay, so the proof is somewhat technical, and I don't want to sort of get stuck in all the details, but I'll just talk about a few of the key points here. It turns out it's sufficient to prove three different components to get our final result. So the first is more a simple observation than something you have to prove, and it's that the pointwise maximum or minimum of any two one-Lipschitz functions is also one Lipschitz. In technical jargon, this means that the space of one Lipschitz functions forms a lattice with respect to these maximum operations. That sounds very complicated, but remember the maximum activation. We showed that this is a one Lipschitz activation function, and it's really doing the same thing, just computing the max and the min of two input functions. The next step is that if I can represent the maximum or minimum of any two Lipschitz networks, like in the class of Lipschitz networks I care about, then I can represent all one Lipschitz functions. For those of you with topology backgrounds, this is just the Stone-Weierstrass theorem acting on lattices, so nothing too fancy, but it turns out this is sufficient to give us universal approximation. So then the final step of our proof is, can we explicitly construct some network which does compute the maximum of two other neural networks or the minimum of two neural networks? If we can complete all three of these steps, then we do have universal Lipschitz approximators. So I'll just look at the last step in a little bit more detail, how we construct this maximum min, and I think gives a little bit of intuition about what the Lipschitz networks might actually be doing in practice. So suppose I have these two neural networks, G and F of X, which have these following sort of weights, W1G and WF1 across with some pre-activations, activations, extra weights, just a standard fully connected network built like diagrammatically in this way. Then I can build the following network, which computes the maximum of these two neural networks. So I'm going to have the same input X to my neural networks, and then I'm going to concatenate together the weight matrices W1F and W1G in the first layer. And note that here we're having an infinity norm constraint, meaning if each of W1F and W1G, their largest row sum is bounded, then if I concatenate them, that's the same sort of supremum, and so these are also obey our infinity norm constraint. So we can do this operation. Similarly, I can sort of add zeros to these weight matrices. That won't change the row sums. I'm just adding zeros. So this also obeys the infinity norm constraint. And what I've really done is stack these networks together such that at this layer here, my network just computes F and G in a vector. And then I can apply my maximum activation, pick which one I want with some simple linear map, and then I'll output the maximum or the minimum of these two functions. OK, but this gets onto the question that was asked just a moment ago, which is our construction here needs infinite width and depth. So every time if I wanted to compute the max now of H with some other network, I have to stack things up, adding width, and I have to add an extra maximum activation on the end, adding depth. It turns out this isn't necessary. So here our construction uses maxmin, but a paper from E.J. Cohen and others, the same group as the original Huster paper I mentioned, showed that actually using full sort, so sorting the entire activation vector, is sufficient with only 3 layers, which is somewhat surprising, I think. But actually, we sort of saw hints that this might be the case earlier. So this was a table that Jem showed earlier on in the talk, where we saw that full sort was able to solve this problem perfectly, while maxmin sort of required increasing depth to do better. And actually, you'll notice that the depths here start at sort of 3 and 7. And we put this table out there before they published their results. Just maybe we sort of picked the magic number in terms of depth and happened to find these universal approximators for the full sort networks. So we proved universality, but we haven't proved it for 2 norms yet, actually. So we have some limited progress and some like soft results that we haven't published, but no sort of formal proof. And I think we're still pretty excited to try and figure out what this looks like. And we do believe this result holds. OK, so finally I'll talk about empirical results. How much time do I have? OK, I'll work quick. I'll assume some of the background that Roger gave. OK, I think 2 is reasonable to get through the most exciting stuff, and then I can go from there. OK, so we've already seen adversarial examples. I've just given a slightly different example to the one Roger gave, which I think is kind of fun. So this is from an OpenAI blog titled Attacking Machine Learning with Adversarial Examples. And here they take an image of a dishwasher, apply some adversarial perturbation to it, print it, take a photo of it on their phone, and then show that they can the adversarial perturbation still persist across this like real-world, like noisy printing process. So this sort of emphasizes that there is still something deep and interesting going on here. I'll also point out we're going to use the same threat model that Roger discussed, which maybe has some flaws in the most realistic, but it's still a really interesting setting to study robustness in. So in particular, we're going to consider perturbations of some inputs where the perturbations are bounded in infinity norms, say. So this has already been discussed a little bit, so I'll move fast through this. But I'll just reiterate something Roger discussed a little bit, which is that if we have some margin of our network, and if we have a Lipschitz constraint, then we can guarantee robustness to all adversarial perturbations within some epsilon norm ball. So I've swapped around the notation slightly compared to what Roger had, but this is the same statement that he wrote down before. So then the one way we can utilize this in practice is we're going to train our networks with our Lipschitz constraints and use a loss function that maximizes these margins. So hinge loss is sort of a famous canonical way to do this. Turns out we can generalize hinge loss to multi-class functions in a few different ways. I won't get the details here, but if you are interested, I'm happy to talk offline, or you can check out our paper. OK, so assuming relevant background, I'll move ahead to talk about some of these results. So this plot shows the empirical robustness of these Lipschitz networks over varying perturbations. So the x-axis shows me increasing my norm ball that I'm searching for my adversarial attacks in. And the y-axis shows the accuracy on the sort of adversarial examples I find within that radius. I won't sort of say too much about how I'm finding the adversarial attacks. I'm just using a fairly strong method that we carefully tuned to make sure we didn't have anything too funky going on. And I'll sort of walk through which of these curves should be looked at each point. So first, these sort of slightly transparent curves correspond to the standard accuracy of my networks with ReLU and max-min activations without any Lipschitz constraints. I just swap out the activation functions and I train them normally. And I see that I get pretty severe drop-offs in accuracy for even small perturbations. In red, I'm showing what happens if I use ReLU activations with our proposed norm-preserving linear layers. And we do much better than if we had compared to the standard network, but we still fall off pretty sharply compared to the blue curves, which correspond to training with max-min. And the reason we have multiple curves in each color is because I'm testing with different margins, which sort of trades off clean accuracy versus robust accuracy. And the last curve I'll talk about is these curves in black or gray, which correspond to sort of a standard baseline, which is pretty hard to beat in the literature. So it turns out empirically we have slightly worse clean accuracy, but sort of we're more robust to large perturbations than they are. But there's an important point to make here, which is that this baseline doesn't have any formal guarantees. So while it, in practice, gives us robust networks, it's sort of an ongoing question of can we verify these networks are robust? And no one, as far as I'm aware, has been able to do that yet. Whereas for our networks, we can get these formal guarantees. So here I'm showing these theoretical robust lower bounds for these networks. This means that no adversary in existence will be able to force the accuracy below these curves for these networks. Now note there is a pretty significant drop-off compared to our empirical robustness. That could be a consequence of one of two things, we think. One is that these lower bounds are just a little bit pessimistic. The other is that maybe our adversary isn't quite strong enough to find attacks that work well. But in any case, this still tells us no adversary will be able to beat these thresholds. Okay, I'll also show some results quickly on the convolutions. So first, just to verify, this is 4 different methods for producing Lipschitz convolutions. Some we propose in our work, some have been explored before, and things in between. And this approach is verifying that BCOP, the method we propose, using using the Bjork algorithm, does achieve exactly singular values of 1 everywhere. So we can, in practice, achieve this desirable property that we have norm-preserving linear layers, or convolutions. So we've compared the robustness and clean accuracy of this thing compared to these other existing approaches for producing Lipschitz convolutions. Okay, yeah, I'll wrap up very quickly. The short is BCOP sort of dominates all other approaches we've seen so far, and actually also beats the state of the art for provable adversarial robustness on MNIST and CFAR, which, while simple data sets, are still very challenging for this problem. There's also one exciting thing I'll just use at my last 30 seconds on, which is the benefits to interpretability, which is something that maybe isn't immediately obvious this would happen. So here I'm plotting sort of a saliency map of the input gradients for a standard network. At the top, I'm showing the relative input, and as I move down, I'm taking the gradient of the output logit for a particular class with respect to the input. So the diagonal corresponds to, so let's just look at the 0 column. At first, I'm saying what change do I have to make to my pixels to maximize the probability of being a 0? And because the network is achieving more or less 100% accuracy, it says basically nothing. This is already like a perfect 0. And I can see, what about asking that same question for trying to force it to be a 1 or a 2 or a 3? And it turns out that the sort of pixel mask I add in each case looks more or less the same. There are sort of some high-frequency deviations, but actually the gradients aren't very informative. They don't tell us anything about the learned network. However, if I do this same procedure for a Lipschitz-constrained architecture, if I now look at the 1, for example, I see that in the first, if I take the gradient of 1, if I try and force 1 to look like a 0, this sort of adds a gradient mask, where in blue, I'm adding in pixels where the 0 would be, and in red, I'm subtracting the 1 pixels. And this happens again for like 2, 3, 4, 5. So actually, without doing any sort of nice conditioning, the Lipschitz constraint automatically gives us this interpretability and nice landscape properties. Okay, so I should, of course, say, give due credit. The first paper that we've spoken about mostly today was Jem, myself, and Roger. And then the other paper I mentioned is titled Preventing Gradient Attenuation in Lipschitz-Constrained Convolutional Networks. And the wonderful people that worked on this paper can be seen here. So the people that aren't here today are Kuyang Lee, Samuel Hack, and Jörn Jacobsen. And thank you very much.